I'm not strictly speaking going to be talking about, you handle the volume from wherever you are. I'm not going to be talking about geoengineering as such. I think I'm going to be talking more about why you might actually want to consider geoengineering in your toolkit. And the main point I want to make tonight is that limiting climate damage ultimately means zero emissions of carbon. But most of the truly zero carbon options we have today are at present either not scalable or too expensive. That means we're going to need a lot of innovation to get where we need to go. But in addition, we're likely going to need some damage control, which is at least how I think about geoengineering. So let's start with why zero. Think of the climate as a bathtub that has a limited capacity. We're pouring about 35 billion tons of CO2 into the atmosphere right now, into the bathtub, and we're only draining several million tons per year out of the bathtub. It's pretty obvious what's going to happen to the water level in the bathtub over time. Another way of thinking about this is that CO2 is essentially forever. That is, every molecule we put into the atmosphere is going to be there, at least 3/4 of them are going to be there 1,000 years later. This is a pretty typical depiction of decay of CO2 over time. And as you can see, on the y-axis is CO2 concentrations in parts per million. X-axis is time. So here we are around 2010. And even if we stopped emitting all CO2 in, let's say, 2100, you would have this kind of tail associated with those emissions out to like the year 3000. If this is a point that's not well appreciated, is basically there's a lot of inertia in the system, which means that you kind of have to account for every molecule you put up. What that means, if you think about it from the other standpoint, is what do you have to do to prevent the bathtub from overflowing? Well, you've got to shut the spigot off. If you're not draining very rapidly, although there are some ideas on the table about draining through air capture, which maybe Jason will discuss or not later. Basically, you're stuck with it, so you've just got to shut the spigot off, which is what this represents. This is a pretty typical curve showing what you have to do by, say, mid-century with your CO2 emissions in order to, say, have a decent chance of stabilizing climate at 2 degrees above pre-industrial levels. You have to go to zero. It's sort of arithmetic, basically. The problem is that we're going the other direction. So this is world energy demand as projected. This happens to be a BP chart, but you can get the same thing from the International Energy Agency to 2030. And as you can see, we're talking about basically a 2-time increase, a doubling of energy demand. But notice also that most of it's fossil fuels, with a very little bit of renewables on top, hydro and so forth. So we've got this huge burden. Most of that growth is going to occur in the developing world. This is a graphical depiction of where the growth in energy is expected to occur to 2035, with the regions distorted by volume. So it's proportional to the energy growth. And you can see the real action over the next few decades is in India, China, the Middle East, and to some extent Africa. Europe and the US are a bit of a sideshow when it comes to energy growth. So you've got this problem of intense growth combined with a lot of fossil fuels. Just to give you an example, the China coal fleet versus the US and the EU coal fleet. Here's the EU today, here's the US today, this is China today, and what happens over time is that China continues to grow substantially. These are projections from various Chinese agencies. And as you can see, we'd be lucky actually, in this case, probably the US and the EU will drop somewhat. We're already seeing some retirements in the US. But keep in mind, most of these coal plants are going to be less than 25 years old, 15 years from now, so it's unlikely that anyone's going to bulldoze them. We're still running coal plants in the United States that are 40, 50, 60 years old. So that's a problem we have for a very long time. So what would it take to get to zero? What on the solution side? Well, just to put it in one way, is that we need about 30 terawatts of carbon-free energy on the planet by 2050 to deal with a 3-time energy growth and need to decarbonize. What do we have? How does that compare to the energy system we have today? Well, here's our coal. This is oil. This is gas. This is nuclear. And that's hydro, biomass. So as you can see, we basically, most of our system is fossil. We've got a little bit of non-fossil. but we've sort of got to double all of that and make it all zero carbon. So what does that mean we've got to do? We've got to replace Earth's energy infrastructure with zero carbon energy, and then we have to double the size of that zero carbon infrastructure. No big deal. What does this mean? Decarbonize all electricity generation, shift all transportation to electricity or zero carbon fuels, shift all industrial processes to electricity or zero carbon fuels, shift all buildings to electricity for HVAC and do it with zero carbon. Do all this in 45, 50 years starting now. So how realistic is that prospect? Well, what are today's zero carbon energy options? Let's look at that. And I'm going to confine my comments tonight to electricity because as bad as it is in electricity, it's even worse in transportation and industry. So this is the best case. We have energy efficiency, we have wind, we have solar, we have biomass, we have other renewables, we have carbon capture and storage, which is scrubbing fossil fuels with carbon, we have nuclear. Let's just take those one by one. The problem with energy efficiency is great. I spent 12 years of my life pushing it, but it's not gonna negate all that demand. Let's go back to our 2 to 3-fold increase in energy demand in China and India. Another way of looking at this is you can't conserve your way out of this problem. I mean, basically, you're going to have an absolute increase in demand. The only question is how much. Just to give you a feeling for where the scorecard stands, this is total energy consumption per capita on the y-axis. On the x-axis is population. We have various countries. So North America is way up here. India, Africa, other parts of Asia are down here. Here was China in 2003. Here's China today. So you can see they've already doubled. It's basic history that as you go up the development curve, you use more energy. That's Bulgaria, basically. So if we can assume that India, Africa, Asia, China are going to get at least to Bulgarian levels, that's a lot of demand, increased demand. I don't care how much you chop down demand in North America. There's a lot of absolute demand. Just to give you a simple illustration, let's look at room air conditioner purchases around the world in 2010. Well, that was the US and that's China. So we could make all of China's room air conditioners 50% more efficient than they are today, but the demand is still going to be 8 times more than the incremental demand in the US. So I'm not saying efficiency is not real important. I'm just saying that it's going to be a marginal utility. Just to give you a feeling for what most of the studies out there assume that are really aggressive on this, they say, well, here's business as usual demand, but we'll get rid of a lot of that by efficiency, and that's what the real trajectory will look like. But recent history tells us differently. This is actually a plot of annual change in energy intensity, that is, amount of energy per unit GDP, and this is over time. And as you can see, we sort of bounced around at our best at about 2% per year annual improvement. And now we're going backwards, in part because China and other parts of the world are coming on stream and having more energy-intensive industry and lifestyles. This is what's baked into most of the mainstream studies. They're assuming it will sort of, be at about 1.5% to close to 2, and then these are the really aggressive studies. So, decide what you think is realistic here. That's increasing intensity dipping above the line, decreasing intensity below the line. This is the best that California ever did. California is generally held up as the poster child for energy efficiency, and they've done an awful lot. But the best they ever managed in the electric sector was something like 1%, a little bit less than 1% per year. So they're really off the charts. That's the best we can do. We're not going to make it. Let's talk about wind and solar, 2 other things I love. But let's talk about their challenges and why at least in my opinion, they're unlikely to scale to a level of being a dominant solution set, at least on current technology. Let's just start with the fact that they don't have much power density, and you need a lot of them to create power. Just to give you a feeling for this is the total global output of photovoltaics in 2011 in terawatt hours. That's 3 months worth of new China coal plants. Okay, so we can do a lot of PV, but the fossil is growing much faster, and we can get into the reasons why. Another example would be wind, another project I love, the Cape Wind Project, but it's 25 square miles of ocean. It produces about 170 average megawatts per year, less than 1 gas turbine, which takes several acres and 600 average megawatts per year. Another way of thinking about this is to do 1 nuclear plant's worth of power output, you need 5 Cape Winds. And the demand of just say New England power demand is somewhere around 25 large nuclear plants. So you do the math. and tell me whether you think wind is a scalable solution. You know, I'm not saying that it's not part of the solution. I'm just saying that those who argue that likely that solar and wind are going to provide most of our solutions are not really looking at this in a realistic way. The other problem with our solar and wind is that they have quite variable output and to a certain extent unpredictable output. The top is a plot of wind output over a period of days. The bottom is Texas wind. There's the installed capacity in August, and then there's the actual output for a lot of August. It doesn't blow very much down in Texas in August, and that's an issue. A number of studies have been done of what would be the cost of trying to provide all the backup power for all the wind and solar. This is a plot of several studies, and as you can see, the kind of multiples you get from the first unit up to, say, 20, 40% penetration is, say, two to threefold cost increases. So you can do it. I mean, you can build all that extra gas capacity and nuclear capacity to back up the wind, but it's going to cost you a lot. Just an example, just about a year ago, National Renewable Energy Laboratory came out with their Renewable Energy Future Study, which said renewable electricity generation for technologies that are commercially available today, in combination with a more flexible electric system, is more than adequate to supply 80% of total U.S. electricity generation in 2050 while meeting electricity demand on an hourly basis in every region of the country. It sounds great. Now let's look under the hood. Less than 50% of that was wind and solar. It included 100 gigawatts of new hydro, which is the equivalent of 50 Hoover dams, 100 gigawatts of biomass, which is not going to be carbon neutral. We can get into that later. 150 gigawatts of energy storage, which doesn't really exist yet at commercial scale, aside from pumped hydro. We have to double the size of the U.S. transmission system and eliminate all load growth, and it still doesn't resolve to the sub-hourly levels, which is where this really matters. It's not so much the hourly. If your power fluctuations on the system at even the second level is a big deal. So turning from renewables and efficiency, what about some of the other options? Carbon capture and storage, which is, I won't go into in great detail, but certainly something that has been commercially demonstrated for gas and coal. In very simple terms, you're extracting the carbon from flue gas, or you're eliminating the carbon before the gas is burned in the turbine. This is an example of one such project in Mississippi that has demonstrated this technique. There are two large coal carbon capture storage plants underway in the U.S., one in Texas and one in Mississippi, but there are additional costs, maybe as much as 50% over the cost of a conventional coal or gas plant. Also, there's a large infrastructure scale-up that would be required to sequester all carbon from fossil plants, probably equivalent to the global oil industry in terms of the amount of fluid handled per day. Not impossible, but definitely a challenge. And I'll just skip ahead. Nuclear, it's especially a bitter irony for me since I started my career fighting nuclear plants. But looking at this objectively, nuclear does have some distinct advantage in climate in trying to solve the energy problem. First of all, its base load, like CCS that it is, doesn't have a fluctuating, in fact, quite the opposite. Nuclear plants run much better, as close to 100% capacity factor. So you get the base load, you don't have to compensate for the variations. It's plug and play into the existing grid. You don't really need to do a lot of grid modifications like you do if you're going to have dispersed wind and solar. Very power dense, relatively few sites needed compared to say the number of sites you need for wind and solar. Not a lot of infrastructure requirements. The disadvantages are well known. Cost. Now that's that's an interesting and moving target. I would say yes, cost has been the big problem in the United States. It's very interesting though. China is building 30 reactors as we speak, and South Korea is building them all over the world. Someone thinks they're cost effective, at least by comparison. And China, in fact, pays probably far more for, say, for example, gas than we do, probably 4 or 5 times what we do for natural gas. So while clearly nuclear is not economic in the U.S. right now compared to a cheap combined cycle gas plant, it's probably quite cost effective in China. And China is beginning to scale up its capability to build these things. We'll talk about that later. Current light water designs, which is the design that we locked into in the 50s, are fragile from a safety perspective. Obviously, Fukushima is a good example of that. No one died at Fukushima from exposure to radiation from the nuclear plant, but it certainly scared people and resulted in the shutdown of the rest of the Japanese nuclear plants. So, you know, we can argue about what are the relative risks of nuclear versus fossil or anything else. The reality is there's at least a perception problem around the safety of current designs. There's the issue of nuclear proliferation, weapons proliferation from spent fuel. And then there's, of course, the waste disposal issues. Again, we can argue about the severity or not of those, but they are public perception issues at a very minimum. This just shows you the sort of distribution of current reactors underway around the world, with China leading the pack, Russia, India, and on up. So it's not a dead industry. Some of the advanced nuclear technologies may avoid some of the disadvantages of the current light water reactor platform. This is an example of a small modular plant. This is, as opposed to the traditional plant, which might be 500 to 1,000 megawatts, this would be like a 200 megawatt unit. It can be put on the back of a flatbed truck, taken to a site and bolted to the ground. Very different, basically manufactured in a factory and then taken to site. Very different than the one-off, bespoke, custom plants that we've been designing, that we designed in the United States. So that's one example, is shrink, modularize, and therefore control costs. There are better reactor ideas out there. This is a company that's basically called Transatomic Power, which is based right here across the river. And it takes existing nuclear waste, which has 97% of the energy value still left in it, and burns up that waste and uses it as fuel in a molten salt compound. And molten salt has all kinds of advantages over water. For one thing, it won't boil off like water does and run you into the kind of problem you had with Fukushima and 3 Mile Island and that sort of thing. Another example is the advanced gas pebble bed reactor, where gas is the moderator for the reaction rather than water. And this is an example of a plant being built right now in China. You'll notice the theme here. China's taking the lead on a lot of things. So cost, of course, can be a challenge for all the zero carbon options, and this is probably the principal reason why we're not moving forward. What's the bogey? Well, this is a gas combined cycle plant, and I'm just looking at the internal cost for a moment, not about the system cost, this problem of intermittency that we spoke of. So that's a gas combined cycle plant. That's the existing coal plant running costs. That's a gas combined cycle plant with a $20 carbon tax, $20 ton carbon tax. There's nuclear. There's onshore wind, looks pretty competitive, at least compared to nuclear. But there's carbon capture for an integrated gasification combined cycle plant. There's a retrofit. That's offshore wind and that's solar PV. So you can see you got a pretty big delta in here. Even just looking at the costs at the bus bar, that is out the plant. However, batteries are not included. And other integration costs. So when we look at these, this is not a strictly apples to apples comparison. Going back here, the offshore wind, solar PV, and the onshore wind do not include the very significant costs associated with integrating them into the grid. So what is to be done? Well, first, I hope you've taken away from this talk, if nothing else, that we probably can't afford to take any of the options off the table. I started out as an energy efficiency guy and wind guy, and through learning, I've really come to the view that if you're going to really get to zero, you can't afford to take any of these options off the table. Second is substantial research, development, demonstration is going to be needed, just to give you a feeling for how really woefully behind we are on this. U.S. energy RD&D, public RD&D is about 5% of U.S. defense RD&D, and that has to change. And finally, prepare Plan B, C, D, E, F, all the way to Z, which is what these guys are going to talk about in a minute. Because I think we're going to need a spare plan. I'll just finish with my favorite version of geoengineering because it's so reversible. This is a nonprofit corporation on whose board I sit called ICE 911. Very simple concept, which is the Arctic's melting very fast, and it's a really positive feedback loop in which as ice melts, water gets darker, attracts, retains more energy, temperature rises, more ice melts, the ocean gets darker, more heat, and so on and so forth. This is just a concept that would involve, these are silicate balls that are made of very reflective material, biodegradable, put into sections near ice flows. You could also do this on glaciers. Reflects energy back into space and cools surface, or at least prevents heat from being retained. You know, science fiction, yes, at some level. On the other hand, the Arctic's going pretty fast, and it's interesting that I could share with you the calculations, but it's not like you have to cover the Arctic with this stuff in order to make a difference. I mean, you know, thousands of square kilometers would actually make a measurable difference. Are we ever going to do this? I don't know. That's for the next guys to answer. It's all in there. Okay, thank you very much.